I welcome you once again to Physics Medicine online tutorial class. You're welcome once again. Now remember, in our previous class we talked about the formation of images by curved mirrors, and under it we saw ray diagrams of images in a concave mirror and that of convex mirror. At different positions of the object, we started when the object is beyond C, that is the center of curvature. We saw the nature of image we produced. We talked about when object was at C, that's the center of curvature, where the image is also the same size as the object and the image is formed at C. We saw when object was placed between F and C, an object placed at F. We equally saw when object was placed between F and what? P. And that is the only situation when object is placed between F and P, that is the pole. That is the only situation in a concave mirror where we produce an enlarged, erect and virtual image. Remember, virtual image that you cannot get on the screen. We equally talked about the ray diagram of a convex mirror, where we say despite the position of the mirror, despite the position of the object to the mirror, you will get the same nature. We say that the image is formed behind the mirror. The image is a virtual image. You cannot see it on the screen. The image is upright, erect, and also diminished. We equally talked about our mirror formula, where we have that 1 over U plus 1 over V is equals to 1 over F. Then we saw the sign convention. Real is positive and the new Cartesian. Then we equally saw linear magnification, which we say we can calculate by using the formula linear magnification M equals to what? V over U. That is image distance over object distance, or image height over object height. Remember, linear magnification does not have what? Units. Now today we are going to take some examples under this mirror, curved mirror. Example 1, we are going to repeat it again. An object is placed 10 cm in front of a concave mirror whose radius of curvature is 12 cm. What is A, image distance, B, magnification, C, the nature of the image? Now let's see. Here we want to use the sign convention of what? Real is a positive. Now in this case, we were given the radius of curvature. And remember, we said that F, which is our focal length, F is equals to R over 2. This is 2. So we have, and for a concave mirror, the focal length is always a positive. According to our sign convention, real is positive. So here I have 12 over 2. So my focal length F here is what? 6 cm. Then we are giving the object distance to be what? 10 cm. That is U. Now remember, we are looking for the image distance V. We use our mirror equation. 1 over U plus 1 over V is equal to 1 over F. We are going to make 1 over V the subject. 1 over U will cross this side and become negative. So I have 1 over F minus 1 over U. Now that is 1 over 6. 6 is for my F minus 1 over 10. 10 is for U. I'll find the LCM of 6 and 10. And that will give me what? 30 at the denominator. Now 6 into 30 will give me 5. 5 times 1 will give me 5. Minus 10 into 30 will give me 3. 3 times 1 will give me 3. So I have 5 minus 3, which is 2 over 30. And that is 1 over 15. Remember, we are looking for V, not 1 over V. So V becomes 1 divided by 1 over 15. That is 1 times 15 over 1. And our V here is plus 15 cm. So our image distance is how many? 15 cm. Our image distance is what? 15 cm. Remember, we are looking for image distance, magnification, and the nature of object. Now let's look at our magnification B. B says magnification M, the formula is V over U. We have gotten our image distance now to be 15, and our object distance was given as 10. So 15 over 10 will give us 1.5. So you find that magnification is 1.5. That means the image is magnified. Assuming magnification is 1, that means the image is the same size as the object. And if magnification is below 1, that means image is diminished. Now the other one is using new Cartesian method, but I advise you just be using real is positive. Now C says the image from the nature of the image. So the image will be what? Real. You can get it on the screen. That is why it is positive. Magnified and what? Inverted. Magnified because you saw the magnification to be 1.5, and inverted. Thus, we obtain the same result, whatever the convention sign we use. Now, let's go over to example number 2. Example 2. A concave mirror of radius of curvature 20 cm produces an inverted 3 times. Produces an inverted image 3 times the size of the object. 3 times the size of the objects. Now, placed on and perpendicular to the axis, calculate the positions of the object and the image. Calculate the position of the object and the image. We are looking for U and we are looking for V. Let's take it again. Now, remember, we are still talking about a concave what? Mirror of radius of curvature 20 cm produces an inverted image 3 times the size of the object. So image is V. So V will be equals to 3U. U is object. So we have image that is 3 times the size of the object. So meaning the image is magnified. Now the question says we should calculate the position of the object and the image. We are looking for U and V. Now we are giving radius of curvature to be 20 cm. That means our focal length F will be R over 2 according to our formula. Now 20 over 2, F will be 10 cm. Now we go over to the mirror formula. 1 over F is equals to 1 over U plus 1 over V. Let's substitute. 1 over 10, 10 is my F, will give me 1 over U plus 1 over V. Remember my V now is 3U. So 1 over 3U. Now, I will have that. I'm going to find the LCM of U and 3U. And that will give me what? 3U. U into 3U will give me 3. 3 times 1 will give me 3. Plus 3U into 3U will give me what? 1. And 1 times 1 will give me 1. So 3 plus 1 will give me 4 over 3U. So I'll come back to my formula. 1 over F, which is 1 over 10, is equals to what? 4 over 3U. That means I'll do cross multiplication. I will have that 3U will be equals to 40. Then what is U? 40 over 3. So my U is 13.3 centimeter. That is my object distance. Now, what is my image distance? I can still use this formula to do it, or I can just use this equation where I say that V from the question is equals to 3U. V will be equals to 3. I'll substitute for U, 13.3. So V is equals to 40 centimeter. So you find out that your object distance is 13.3 cm, while your image distance is 40 cm. Let's go to example 3. An object is placed 15 cm in front of a convex mirror. In front of a convex mirror. Now we are talking about what? Convex mirror. And an image is produced 5 cm behind the mirror. You can see that for convex mirror you have a vitral image. Image is formed behind the mirror. Calculate the focal length of the mirror. We want to find the focal length of the mirror, F. Now what do? Let's see what is given. We are given object distance to be 15 from the question. Then the image distance, please, this is minus 5, not minus 15. The image distance is what? minus 5. The image distance is what? Minus 5, not 15. Why negative? Why minus? Because we are talking about convex mirror, and convex mirror always produces a virtual image. So virtual image, according to our sign convention, we replace it with what? Negative. Now we use the formula because we are looking for the focal length. 1 over u plus 1 over v will give me 1 over f. Now 1 over 15, that is u, minus, because this minus 5 minus plus we turn to minus 1 over 5. Please, this is 5, this is 5, not 15. Plus, sorry, minus 1 over 5, minus 1 over 5. Then is equals to what? 1 over what? 15. Sorry, is equals to 1 over f. Now let's see. Now we are going to look at this. 1 over 15 minus 1 over 5 is equals to what? 1 over f. Now we find our LCM. What is our LCM? Our LCM will be what? 15. So 15 into 15 will give me 1. 1 times 1 is 1, minus 5 into 15 will give me what? 3. Then 3 times 1 is 3, is equals to 1 over f. Now 1 minus 3 will give me minus 2 over 15. So minus 2 over 15 will give me 1 over f. And if I want to find f, f will be 1 divided by minus 2 over 15. That is 1 times 15 over minus 2. And that will give me minus 15 over 2. My f become minus 7.5 cm. So you can see you have also a virtual focus. For a convex mirror, as we saw it practically, the image, you cannot see it on the screen. Now let's go over to example 4, and that should be our last example here. Example 4. And let's see example 4. An object 7 meter high is placed 15 cm from a convex spherical mirror, convex again, of radius of curvature 45 cm. Determine its what? Image. Determine its what? Image. Now we are given the height of the object. Object height, take note, 7 meter. Then it's placed 15 cm from a convex spherical mirror. The object distance is 15 cm. Then radius of curvature r is 45 cm. That means f will be 45 over 2. You add negative because convex mirror has a virtual focus. So my f becomes minus 22.5. We're going to find v. Now 1 over f is equals to 1 over u plus 1 over what? V. Then we now have 1 over f minus 1 over u will give us 1 over v. Remember, we are determining the image. Now 1 over my f is minus 22.5 all over 1 over my u, which is 15, is equals to 1 over v. Now you find your LCM the same way. Now the LCM is 22.5. Then let's go. You have 22.5 into 22.5. It will give you 1. Then 1 times 1 will give you 1. That is minus 1. Then minus 15 into 22.5 will give you 1.5. 1.5 times 1 will give you another 1.5. So I have minus 1 minus 1.5, and that will give me minus 2.5 all over 22.5, and that is 1 over v. So what is my v? My v becomes minus 22.5 all over 2.5. And when you divide it, v will give you what? 9 cm. Our v will give us what? Minus 9 centimeter. It will give us what? Minus 9 centimeter. Why minus? Because it is a virtual image. It is what? A virtual image. Then we can equally find the magnification, because we are asked to describe the image. So you find everything about the image. Magnification is view over U. You don't include the negative. The negative is just telling you whether the image is real or virtual. So my V is 9 cm divided by U, 15 cm. Cm we cancel cm, and 9 over 15 will give you 0.6. Remember I told you magnification has no units. So you can see 0.6. The image is not up to 1. It's diminished. We can equally find the image height. Remember magnification, another formula says image height over object height. So we use this formula to get the image height. Now magnification is 0.6 is equals to image height over, from the question we are given the object what? Height. Look at it. Produces an object 7 meter high. So we are given the object what? Height. So that is image height over 7. Cross multiply to find the image height. Image height will give me 0.6 times what? 7. And that will give me 4.2 centimeter. You can see the object height is 7 cm, while image height is 4.2 cm. That will tell you that the nature of what? Image formed by a convex what? Mirror. We say the image is what? Diminished. So you can see that the image is virtual. You form it at the back of the mirror or behind the mirror. Image is erect or upright, 9 cm behind the mirror, and 4.2 cm high. And the height of the image is 4.2 cm, showing the image is what? Diminished. Now let's see the practical applications of this curved mirror. How do we apply it practically? Number 1, concave mirrors, they are used as shaving mirrors. That is true, because when a man places his face near the mirror, that is between your principal focus and the pole, you are going to obtain an enlarged and erect image, and the image is also virtual. You cannot get it on the mirror, but you cannot get it on the screen, but the image is formed behind the mirror. That's why you see your face. When you look at it, your face become erect and upright. Your face will not turn upside down. Number 2, concave mirrors are used as reflectors in reflecting telescope and what? Microscope. Another one used is that convex mirrors are used as driving mirrors of motor cars. We all know that we use them as driving mirrors because they will give an erect image of the object behind the driver. When you are driving, you look at the mirror in front, you'll be seeing the object at the back. But in addition, such convex mirror, they provide what? A wide field of view. Therefore, objects within a large angle can be seen with the help of the mirror. So object that is very, very far away, using that mirror, when you look at the mirror, you will see that object behind. Very far away, you'll be able to see them. Now we've quickly look at parabolic mirrors, which is a special type of curved mirror. A special type of curved mirror is the parabolic mirror. Now, as the name suggests, parabolic mirrors are in the shape of the tip of what? Parabola. The shape is like that of what? Parabola. Now, what happens here is that parallel rays from a distance u, very far away, infinity, can be brought to focus on a single point by using your parabolic. Let's see. Now look at the incident rays coming from object. The object, you are not seeing them. Object is at infinity, very, very far away. Now you see parallel rays of light coming from infinity, very far, striking this mirror, it will be reflected back. Another ray of light striking the surface of the mirror will be reflected. Another incident ray striking this mirror will be reflected. You can see the arrow showing they are reflected. Another incident ray coming very far away from infinity, striking the mirror, will equally be what? Reflected back. Now you find out that all these reflected ray, look at another incident ray striking this mirror, will be reflected back. They will converge at a point. to produce a single what? Focus. Now, parabolic mirrors, they have many applications because of their ability to converge rays onto a single point of focus. So these rays, they converge them at a single point. So they are used in, number 1, reflecting telescopes, number 2, satellite dishes, and number 3, we use them in your car headlights. Your car headlights, we use it to see very far in the night. Now, in reflecting telescope, light rays from distant stars and galaxies, they are brought to focus on a point before they are being reflected. In satellite dishes, the focus microwaves instead of light onto what? A single point. Then in car headlamp or headlights, they utilize the convergent property of parabolic mirrors in the reverse. A light source is placed at the focus of the mirror. The light rays from the source are reflected by the parabolic mirror into a parallel beam which illuminates the road. So these are the applications of these parabolic mirrors. We use them in reflecting telescope, we use them in satellite dishes, and we use them in our car head lamp. Now we have come to the end of today's class. Now let's look at our evaluation question. You evaluate yourself with this question. Number 1, with a ray diagram, describe the image of an object placed at the center of what? Curvature. Remember, you don't need to cram this. With the explanation, you draw its appropriate scale, you will get the nature of the image. Number 2, state 2 uses of concave mirror and 1 use of convex what? Mirror. 3, state 3 applications of parabolic mirror. Number 4, a concave mirror of radius of curvature 40 cm is to be used to obtain a real image of an object. Where should the object be placed and where is the image to be found? Thank you for your patient listening. See you next time.